My name is Baocheng, and I did my master in Weizmann Institute with Professor Thomas Vedic, and now I'm a PhD student in EPFL. So this is a work I did when I was in Weizmann. It's called Quantum Interactive Oracle Proofs. So I will start the presentation. So a little bit background. So IOP is generalization of PCP, and quantum PCP is also a generalization of classical PCP. So our work is to build a concept that generalizes both classical IOP and quantum PCP. So a brief review of all these concepts. First, you have a PCP theorem, which says give you a classical input X, and a classical verifier want to decide whether X is in NP language or not, and he have access to a classical proof. The length of the proof is polynomial, and he query classical bits, and I mean classical query to this bit, because later we'll talk about quantum query, and to decide whether it's an NP language. And then as analog, you have PCP conjecture. Still, you have an input, which is a classical string, and the verifier is quantum. Now your proof is a quantum state, and the length of the proof is a polynomial, and you do quantum query to constant bits, and to decide whether it's a QMA language. So actually, there are a few versions of quantum PCP conjecture. Like you have multiple way to define it, and we will present. Like later, I will present the way we defined it. So to make the definition process more precise, we need to define. So classically, how you define this thing doesn't matter, because well, it still matter a bit, but the classical verifier in our case, we say it if the classical verifier invokes the following subroutine only once, we say it query S bits. So means give a subset S, you apply a classical algorithm to the bit indexed by S along with some private bit. So this is non-adaptive definition, and for the quantum setup, we also define it in an adaptive way. So you first chose a set S, and then you apply a unitary to the poorest register indexed by S, and together with some private registers. So when I talk about my quantum PCP, it is a non-uniform version. Sorry, non-adaptive version. And then I would like to introduce interactive oracle proofs, where you have which is a combination of IP and PCP. Okay, so it's an interactive proof. You have a classical communication, constant round, polynomial communication, and at each round, the verifier queries constant bit. Right. And moreover, the query set is chosen at the beginning of the protocol. This is just to make the whole protocol very non-adaptive. So even the query set at each round is chosen in the beginning. And the honest prover is efficient and decide whether X is in NP language or not. So classically, people research this for multiple reasons. In the beginning, IOP have two purposes. One is to build a succinct argument. Another is in theory, like for double efficient verification. Right. So yeah, so I'm just saying this is a very nature object to look at for classical. And then I introduce our model, so it's quantum interactive logical proofs as a combination of classical IOP and quantum PCP. And the difference is here you have a quantum verifier, you have a quantum communication, constant round. The communication is still polynomial, and each round the verifier query constant qubit. And still is very non-adaptive. The honest prover is supposed to be efficient, and you need to decide QMA. And a brief recall of our query, because now we have multiple rounds, so things can be a bit confusing. So first of all, the verifier part of the input is for prover's message register, and this subset SI is already chosen in the beginning of the protocol. It has nothing to do with the S round. And then you also have the verifier's private register, and then all the other prover's registers. So that's what I mean by a query. Is this clear? And then there's a very important thing I want to talk about. This makes the setup of IOP and like this issue don't exist classically, but for quantum, it works to think about the difference. So classically, operating a bit is detectable. Say you have a bit, like a register of classical bit, and now you flip it, then it's okay. Say the prover send verifier classical register, the verifier did some change and send it back. So the prover know which kind of change the verifier did. But on the other hand, if the send verifier a single qubit, the verifier say apply some gate on it and send it back, the prover won't know. The prover only have one copy. So this raises the question whether we should allow the verifier to send the prover's message back, because this makes a difference. And at the same time, it shouldn't be counted as the whole message being read, because if you look at the Euro definition of IOP, if the verifier want to send the prover's message back, usually it means the verifier, although it's very stupid, but the verifier have to read the message, then he can send it back. Otherwise, there's no way for him to send it back. But for us, we just don't consider this. Like, that's why I say we should allow the verifier to send the prover's message back and don't count the whole message being read. And
sorry, can I ask a quick question?
Yeah.
Sorry, just to maybe make sure I understand the model, because I don't fully follow. So here, are you saying somehow like the prover sends like a large quantum state, and the verifier is only supposed to act on like a constant number of qubits and then send that back state? Is that what you mean by verifier is sending the message back to the prover? So he has access to like the whole state, but he's just only acting like having it on a few, and then he's sending the whole state back to the prover.
Yeah, yes, exactly.
Okay, thank you.
Yes, and classically doing this is pointless because the prover know which kind of bit you change. But quantumly, if the prover send the verifier a quantum register and the verifier do something, the prover won't necessarily know. So whether we should allow other type of, okay, so basically here I showed one type of the verifier's message is just sending the prover's message back. And actually, what we showed is that if you allow the verifier to send journal quantum message, so classically, when the verifier send the prover some message, this message is chosen by the verifier himself, and it can be anything. But in our case, we show that if you allow the verifier to send arbitrary quantum state to the prover, so it's a general setup, then it becomes kind of simple. So, okay, so by simple, I just mean the verifier pair n EPR pairs and send half to the prover, and then the prover and the verifier going to share n EPR pairs after this first step, and then the prover do a teleportation of the quantum witness to the verifier, and then the verifier can do the measurement on this teleported witness, and then he also need a fix to fix the measurement, and then that's a classical thing you can do with PCPP. And I will also present the exact method later. This is just the result. And the result instead in a more restricted model, strong model, where the verifier is only allowed to return the prover's quantum messages back and send classical messages. So for the classical message, it can be arbitrary message the verifier prepare. But for the quantum message, it's only allowed to return the prover's message. And we also construct a quantum IOP system, except the communication complexity is bad. So just to say, by the definition, a quantum PCP imply a strong quantum IOP, and it's like one round. So it's the best IOP. And another point is, previously we allow a very relaxed model, and we get a result that arguably not so interesting. And here we use a strong model, and we try our best and get a result that in terms of communication complexity isn't so good. So this actually suggests that interesting and easier result may exist in models that are less restrictive. Just a comparison.
Sorry, maybe before we go into the comparison, can I ask, like in this model, what is the intuition of like these classical messages? So what can these actually classical messages be? Because when you talk about like quantum messages, I understand that this refers to, you know, like the quantum prover sends you like some quantum state, then you act locally on a bunch of qubits, and then you send that state back. But what could these classical messages from the verifier encode?
Yes.
Like, what do these represent?
Yeah, so basically, no matter what we do for the quantum part, in the end, we are going to so basically the framework is we have a quantum part and a classical part. The quantum part is to prove the prover have qubit. So for the teleportation setup is very trivial because the verifier is going to do the measurement. So he naturally have the qubit. And if you only and in this strong model, it's a bit more difficult to have a qubit. And once you have the qubit, the prover is going to do the measurement for you. And the prover is going to have the measurement result, but you don't have it. And the measurement result is going to be long, and you need to use PCPP to do the final calculation.
Okay, thank you.
Yes, okay. And then a comparison between the models. The general model, the verifier is allowed to add anything that is standing. Okay, so this is talking about which kind of message the verifier can send. So the verifier can send a classical message, any quantum message also return the poorest message. And in the strong model, the verifier is not allowed to send journal quantum message. And it's a comparison of the result. So for the two model, we both have constant round and a constant query. For the communication, one is polynomial, one is exponential, and in one of the models, the efficiency is polynomial. In another model, I mean, the communication is exponential. You cannot hope polynomial efficiency of the poor, but you can hope some kind of efficiency. So here is like logarithmic test. Okay. Review of related books. So classically, as I mentioned, people research IOP both for crypto reason, also for some pure theory reason. And similarly, we also want to research IOP because it's a relaxation of quantum PCP conjecture. And as this conjecture is not proven yet, so we believe a concrete construction of quantum IOP is going to be inspiring. And also, of course, it have a crypto application too, and we are working on it. On that hand, for IOP, the point is to make more efficient CP. So they cannot really use the whole thing, but they can use the component inside of PCP. And for us, we can use PCP or even PCPP as a whole thing. But we don't really have reference to the tools in quantum PCP conjecture because it's not proven. And on the other hand, it's known that IOP under certain condition, IOP with parameter imply certain PCP exists. And for us, it's not known yet quantum IOP is going to imply quantum PCP. Another point I want to make is the research of quantum PCP conjecture motivate the research of the game version of the quantum PCP conjecture, and specifically the tool of qubit testing, and qubit testing technique also inspire our constructions. And this whole graph. Another related work is, if you think about QMA, is actually in non-deterministic exponential time, which is included in PCP of polynomial randomness, the exponential proof length. So this actually give you a exponential length PCP for QMA, and the proof is even classical. But here the proof is nowhere efficient, close to efficient. And for us, we have some efficiency for the proof. Yeah,
I'm sorry to interrupt.
Yeah.
Hey, I'm so sorry to interrupt, but the audio seems to be coming and going. If you're on a wireless, are you on a wireless microphone?
Yeah, I think so. I'm using AirPod.
Yeah, can you instead of the AirPod in the microphone, can you choose the device's microphone, like your MacBook's microphone directly, or whatever device you're using?
Like use the microphone of my device. Okay.
Yes, because I think the Bluetooth connection is causing issues. I'm very sorry about the inconvenience.
Can you hear me?
Yeah, it's good. It's good. Thank you. Please continue. Sorry for the interruption. Could you please start from the beginning for this slide? That would be very helpful. Thanks.
Okay, so I'm I'm just saying, you have QMA in non-deterministic exponential time, and non-determined exponential time is the same as PCP with polynomial randomness. So polynomial randomness means exponential length proof length. So this actually give you a PCP construction. It's not quantum, it's exponential length, and it proves QMA. So you may argue, what's the point to design a exponential length, like exponential communication complexity quantum IOP? So the thing is, in this construction, the honest prover is nowhere near efficient, and apparently this construction didn't use the quantum witness at all. So in our construction, there's some kind of efficiency for the prover. And another reference, like related work. So we have very similar goal to delegating quantum computation. And in most of the work in delegating quantum computation, both the communication and the verifier are classical, but for us it's quantum. And actually, even if we compare our protocol to a succinct argument, it's still going to be quantum communication and quantum verifier. And they achieve polylog communication. For us, it's exponential. They also use many qubits test from the game version of quantum PCP Conjecture, but they use crypto assumptions. Yeah. And some open question we propose. Whether you can compare quantum IOPs into quantum PCPs. Okay, so this is not clear. Construct quantum IOP under restricted model with polynomial communication complexity. So basically it says, if you keep the definition we made for the strong quantum IOP, can you prove a polynomial communication instead of exponential? And delegate quantum computation under minimum crypto assumptions, say PRU, and this is something that we are doing. Oh, yeah. Never mind. Develop a crypto analogous of the quantum PCP conjecture. Yeah, which means if you have a quantum IOP and you can hope to compile it into one round. So say you are going to have a non-interactive argument for QMA, but polynomial length. So this is kind of crypto analogous of PCP. It don't have like the proof. Instead of a proof, it's an argument. It only have one message, and instead of information theoretic, it becomes computation theoretic. And then you can think about, can you design a proof system for QMA with classical communication? And we ask this because if you look at the construction, it is really quite classical. If we talk about it later, okay. So now we go to the sketch of the proof, and you have questions?
Yeah, I actually have a few questions. So can you explain a bit better this part about like the delegated quantum computation relation? So I have both a question about that point and about the future work, but maybe you can explain a bit this relation.
It's not something deep. It's just saying
I guess, okay, maybe let me rephrase my question. Is there like some relation? So is there like something that from your result directly has some implications on delegated quantum computation? Or it's more the fact that the setting is a bit similar, so some tools might be used in both places?
Okay. Now I remember my point, because usually when people think about delegating quantum computation, is either with two prover and the information theoretic,
Right.
or with one prover but use assumptions.
Exactly.
For us, it's with one prover but without assumptions. But instead, we use quantum communication and quantum verifier.
Yeah, but in that case, don't we already have some candidates? Are you saying that the new thing would be that the quantum communication cost is extremely small?
Yeah, like the thing is, our verifier is efficient. If you do blind quantum computation,
Yeah.
the verifier cost is huge. Also, the communication is polynomial.
Okay, good. So then okay, maybe I can now repeat my question. So does your result already directly give a candidate for delegated quantum computation with a quantum verifier and extremely low quantum communication cost?
We didn't write this in the paper, and we are working on it. Yeah, we haven't write it down. Like I personally believe it already implies one. But we haven't write it down.
Okay,
like,
but you think it's possible?
Yeah, I think it's possible. Yeah.
And in this case, what is this polylog quantum communication? Like, what are the family of quantum? What are like the quantum states being sent in this protocol?
You mean in the other people's delegating quantum computation protocol?
No. I mean in here. So in your proposal, what is like the quantum communication looking like? Like, what are the family of states that the verifier or prover need to send? Is there like some concrete? Yeah.
So basically, we won't use the exponential communication protocol because it's not relevant, and we will only compare the one use teleportation. So So basically, you can say you assume the prover and verifier already share EPR pairs, and then the rest of the protocol is classical.
Yeah, so I understand the part about like the rest being classical. I was just really trying to see like what are the quantum states. So are you saying that because you are using this teleportation?
No. It's like if you assume they share EPR pairs, and then the rest of the communication is classical communication, they don't send the quantum message anymore.
Okay, so you only need to have like EPR pairs being shared between the two parties.
Yeah.
I see. Okay, that's interesting. That's very interesting.
Yeah, and we have another work that just got accepted in CCC. It's a bit different setup. So so in our setup, the verifier the verifier is allowed to send the whole prover's message back, but not allowed to send his quantum registers. And we define a slightly different setup where the verifier is allowed to send part of the prover's message back, and he keeps some of the prover's registers and maybe send them back in the later rounds. So this is a slightly different setup. And in that setup, we have a polynomial communication.
Okay.
And then from there, we also build a succinct argument. Like we're still working on that.
Right.
Yeah.
Okay, that's very interesting.
Yeah.
That's a very nice result. And sorry, maybe one more question on this topic. You had like a follow-up slide after this one. About like some future directions. That you made some observation that I didn't quite follow. So I think in the slide after this one. Yeah. So you also mentioned here something like, again, on the bullet point 3.
Yeah.
So I'm a bit confused because earlier you were saying that you don't need to have any cryptographic assumptions whatsoever, because yeah, you want to achieve information theoretic security with like some let's say quantum verifier and like low communication. So what would be the point of question 3?
Yeah, because in that case, if we keep the particle to be information theoretical, then the verifier need to have a then okay, say the communication is still polynomial.
Okay.
Yeah, and with some assumption, you can make the communication succinct.
So you still want to have like quantum communication, but succinct, and then your claim is that if you want succinctness over quantum communication, you need to introduce some additional cryptographic assumptions.
Yes.
And did I understand correctly that you think that this cryptographic assumption would actually be like a PRU?
Sorry, not for the teleportation one. So for the teleportation one, because everything is classical, I think you need to use like hash clash collision function.
Okay.
Like I think that's the minimum assumption for Markov trees, I think.
Okay.
Like classical Markov tree.
Okay.
Yeah. And for the result we are accepted in CCC, there I think we will use PRU.
So what can you explain a bit the intuition? I don't quite see how the PRU is used here. Like maybe just a few words intuitively, just to see how does the PRU play a role in the task of delegated computation.
So like okay, so basically there's a paper called quantum commitment to quantum state, and then there they give a construction of quantum Markov tree, and the assumption they use is PRU.
Okay, so you are saying that to do this delegation with like log quantum cost, you need to have like some commitment of some quantum state, and then to construct this commitment to quantum states, it's sufficient to have PRUs.
Yes.
Okay, that's interesting. Okay, yeah, thanks a lot for all the answers.
Okay. So now we go to the proofs, and
हेलो कहाँ पे हो भैया?
so apparently we first need a complete problem. So for us, we are going to choose this Hamiltonian, which is a summation of polynomial. Actually, yeah, a summation of polynomial of xz terms. This Hamiltonian is QMA complete if the gap is 1 over polynomial. However, when we want to build a quantum IOP particle, we want to start with a Hamiltonian that have a constant gap. So this one don't, it's not known whether it's going to be QMA complete with constant gap. But anyway, it's useful to believe this Hamiltonian is indeed QMA complete, because what we actually use is more complex, and I will show you later. So for this Hamiltonian, you have a coefficient alpha I, and the L1 norm of the alpha is 1. And say A and B don't have any interaction. Okay, sorry, so the notation XA just means you apply X gate on the place indexed by A. Like, I'm not sure all of you saw this definition, so you have questions? Yeah, okay, I assume like you know this way to define XAZB. Like for example, x001 times z100 is going to be z times z tensor identity tensor x. And okay, so here, yes, so deciding whether the minimum eigenvalue is smaller than exponential or greater than a constant, we assume is QMA complete. Like for the presentation, we assume this. And okay, another thing is here, A and B are not local. That's very important. Otherwise, it will become like local Hamiltonian problem. Like, yeah, like otherwise, if you want the gap to be a constant and you also assume A and B are local, then you directly prove quantum PCP conjecture. Yes. And just give you a classical intuition of what is this Hamiltonian, of this warm-up XZ Hamiltonian. So it can be viewed as an analog of a system of n-linear equations. And you want to decide whether all of this you want to decide whether exactly half of the equation is satisfied. Or like this expectation is greater than a constant. Yes. Okay. And for us, it's more like a quadratic equation amplification. So here you have a system of n quadratic equations, and whether all of them are satisfied or a constant portion is satisfied. Yeah, kind of. And I will present our teleportation-based particle. So here it writes the quantum particle, and I think I will just present the classical analog. So in the first step, the Poorer and verifier share EPR pairs, and the Poorer do a teleportation to send the quantum witness to the verifier. So after the teleportation, the Poorer is going to have two random string A and B. The verifier is going to have the teleported state, which is the original quantum state, but being applied by XA and ZB. So to make things easier, you can think now the Poorer have a uniformly random string R, and the verifier have a string W plus R. And because R is uniformly random, so both Poorer and verifier now is holding uniformly random string in their perspective. And now the verifier want to know a circuit apply on, sorry. Now the verifier want to know a linear product between W and some string. Because now we are using our toy Hamiltonian. The toy Hamiltonian is just a linear system in the classical setup. So you want to know a linear product between W and some string. But here you have R and you don't want this R. So what you do is you ask the prover to first send you something that looks like a commitment. Like, because the verifier cannot just send W plus R to the prover, because in that case, the prover can help you to do the linear product, but then, yeah, the prover can help you to calculate W, but then you also, like, the prover will know which kind of W the verifier is using. So you need to do you first need to do a commitment to send the error correction of R to the verifier using a linear distant error correction code. And then the verifier uniformly sample L from the amplified Ling instance, so linear equation system. And he will calculate L applied on W plus R by himself, and also send L to the prover. And then the prover is going to send the verifier PCPP. It shows that you first decoding E and apply the linear equation plus plus L acting on W plus R is equal to 0. And the verifier checks the PCPP and he's going to know the real result. Is this clear?
Sorry, I have like two quick questions on this. So firstly, in the quantum protocol part,
Yes.
what is like the number of required shared EPR pairs?
What is the number of shared
Like-
EPR pairs?
Yeah, that they need to share.
It's the length of the witness.
Okay, I see.
But this witness is not the original witness. It's like amplified witness.
Right. Yeah. And the second question, can you explain a tiny bit like the intuition of like the use of the error correction code? Like, is it to allow you to do like some fast verifications?
The use of error correction code is because if the prover send R to the verifier cannot read it because we are in a interactive Oracle setup. The verifier can only read constant bit from the prover.
Right. Yeah.
If the prover send R directly, you cannot guarantee the prover is sending you like a fixed stuff. Yeah, and if you send yeah, like, okay, so say the verifier want to use, okay, so basically the verifier need to use R to do some calculation, but only prover have R, and the prover can add some noise to this R. And then okay, so say the verifier want to use a PCPP, and the claim of the PCPP is if the input is far away from some site, the verifier is going to reject with high probability. And you set this site to be the set of input that can make verifier accept. If the set of the input is just plain text, then it's possible there's two strings, they looks very close. but one of them makes the verifier accept, one of them not. And you use error correction code to protect this string.
But then it shouldn't be that any correction code would work, right? You need like some properties.
Yeah,
on
like
this code that you are picking, right?
any error correction code that have a linear distance is going to work.
Okay, I see. Okay, thank you.
Okay. And then I will present our second result. So that's the result that have a exponential communication. So here, I just want to give a framework for verifying communication with exponential communication. So still, we consider this amplified linear equation system. So you have a witness, which is the assignment of the equation. You do a Hadamard encoding and send it to the verifier. The verifier sample a term in the linear equations and accept if only if E is a Hadamard encoding, and then this decoding, like local decoding, like this robust local decoding of the Hadamard code give you, because ELI plus R plus ER is just ELI. So yeah, to check whether the I's linear equation is satisfied. So this is just the framework for, yeah, okay. And then I give a framework to verify quantum communication. So essentially, if you want to verify quantum communication, the verifier first need to obtain the ability to measure many qubits. But in our setup, the verifier only have oracle access, like he can only query constant bit of the prover's message. So he cannot measure many qubits by himself. So he need a test to force the prover to do that. And by many qubit tests, I mean the same thing as in this game version of quantum PCP literature. And then you need an energy test. Say now the verifier have the ability to measure these n qubits. And then he used this ability to do a real measurement to measure the energy. So the classical framework that I just present is a simplified version of the energy test. By simplified, I just mean now you only consider one basis instead of two bases. Yeah.
Sorry, maybe a naive question. So in the classical setting, you were using this classical code with like linear distance that you're explaining. Does it mean that in the quantum case where you're saying that you're coming with like a generalization, you need like a quantum error correction code, or you are still only coding like the classical information with the ACC?
Yeah, like we encoding. So in this paper, everything is encoding like all the code is classical code.
Okay.
Yeah, so later we will just do a Hadamard encoding of the first witness in X basis, either in the Hadamard basis or in the computational basis. So it's like a coherent encoding. Okay, now I'm going to talk about this many qubit test to give a bit review of what do you mean by the prover have the ability to measure many qubits. So Thomas have a lecture note. In that lecture note, he defines what does he mean by a qubit in the context of verifying computation, of course. So when you try to verify a computation in general, you cannot hope to have a arbitrary thing like arbitrary calculation. Usually what you hope is you have X measurement in X basis and measurement in Z basis for a certain state. So in this definition, as long as you have two anti-commuting operator, and it's only these two operators not necessary to be anti-commuting themselves. They only need to be anti-commuting in the sense of the quantum state psi. The theorem says if you have an anti-commuting operator on a state psi, the action of each operator is isometric to X measurement and Z measurement. Okay. And for qubits is similar. So in this definition, for one qubit, you only have one anti-commuting equation. And for many qubits, you are going to have many anti-commuting relationship and linear equation. So basically, this is just the equation of XA and ZB satisfies. And if you satisfy all of the equation for certain state psi, it implies each of these XA and ZB, like each of the operation you obtained is isometric to XA, the real XA and real ZB for some state psi. And that's how you get the ability to measure a qubit. So the framework of obtaining measurement to Pauli operators is just to enforcing the following approximation relationships. And once you have that, you are going to have qubit. You are going to have the ability to measure XA and ZB. So basically, when we design the test, our goal is to have these three equations. Okay, and in the multiple prover setup, how many minutes do I have?
Great. So you have about half an hour, about 35 minutes. So
35 minutes? Okay.
yeah, but you don't, you can pace yourself comfortably. You don't have to use all 35 minutes. It's just an upper bound.
Okay. So if you have two prover, okay, wait. Like say if you want to prove the following approximation relationships, first of all, you need to define what do you mean by OX and OZ. And in this two-prover setup, this is easier because you send the prover a classical string. Say you send the prover classical string A, and without loss of generality, you assume the prover is going to apply a observable and send a classical string back, like send a classical bit back, actually. And in that case, without loss of generality, the prover's action is observable, indexed by A, and it only have eigenvalue +1 and -1 for the two different measurement result. And apparently in our case, if we want this relationship, we also need to find a way to define them. So you hope the verifier send prover XA and ZB, and he is going to send you back the measurement result of OXA and OZB somehow. And somehow you can force the prover to do that. Okay. And for the energy test, it's just the verifier sample a term in this XZ Hamiltonian and send XA and ZB to the prover. And then the prover send you two measurement results back. And the verifier accept if you time the measurement result is the same as the negative of the sum of alpha I. Like if you do the calculation, this is just going to give you the energy. Yes. So still, we need to make our goal a bit concrete. So the framework of our construction have 3 rounds. In the first round, the prover is going to send verifier a coherent Hadamard encoding of the witness register on the computational basis. And then the verifier is going to access one qubit and send the same message back. And in the second round, the honest prover is going to send Hadamard encoding, like coherently, of the same register, but this time under a different basis, Hadamard basis, and send the same register back. And in the last round, the verifier chooses either X or Z, and the prover is going to return back the Hadamard encoding of the same register under the queried basis. And I'm going to present how to do test for a single qubit. So in the single qubit case, the verifier can do everything by himself, but the point is to prove something about how to enforce the prover. Because in the end, without the help of the prover, the verifier cannot go very far. So that's the setup. If you simplify the previous setting, like the many qubit setting to the single qubit setting, then each round they just exchange the same qubit. And in the end, the verifier send either X or Z to the prover, and the prover send back a measurement result of 1 bit. So for the last rounds, okay, 1 second. For the last round without loss of generality.
I'm sorry. Can I ask a quick question? In the general construction that you described,
Yes.
you said you're using a Hadamard encoding of the same register, but in this for the single qubit setting, I think you dropped that, right? You just said it's just the same qubit.
Yes.
So how does it get simplified for the single qubit setting? Right, so for example, for the case of single qubits, maybe you just meant the same thing and I didn't understand. But if you look at the slide, your honest prover setting, sorry, the single qubit setting.
Yes.
The honest prover is sending in the second round.
Yes, sending
computational basis. or is it also in the Hadamard basis?
Oh, yeah, I mean, if there's only one qubit, there's not much difference actually.
Really? Okay.
Well, I mean, yeah, you can think of it as the prover help you flip the qubit in Hadamard basis, but I guess it's more or less the same.
I see.
Yeah, like you can think the prover instead of the same qubit, the prover apply a Hadamard gate on the same qubit. Yeah.
Right, but you're saying it doesn't make a difference whether or not he applies a Hadamard? Is that what you're saying? In the single qubit case?
Because in the multiple case, the first round is to measure the witness in the computational state under the computational basis. So for a single qubit, if you coherently measure in the computational basis, it's the same as you didn't measure it. And for the second round, the prover is supposed to measure the quantum witness coherently under Hadamard basis, which more or less means you apply Hadamard gate on this quantum state and then measure in computational basis. Okay. Here I present in this way is just to make the presentation later easier. Okay, and here if you look at the last round, it's already the end of the communication, and the verifier send 1 bit to the prover. So the prover's action can be formulated by one observable, and you actually cannot do this for the 2 round in parallel. And so we can define the anti-commuting relationship in the last round. And this is our particle. We are going to have 4 tests, and in the particle, you uniformly sample one for the test and do that. So for the first type of testing, in the first round, the verifier measure X, the observable X, and in the last round, the verifier send X. So basically, this is to prove the result of the first round and the third round is consistent. And in the second test, the verifier measure under computational basis in the second round, and in the third round send Z. So this is another consistent test. The third consistent test is a bit weird. In the first round, the verifier apply a X gate, and then in the second and third round, the verifier measure like under Z basis. And the fourth test is more or less the anti-commuting test, because in the first round, the verifier measure under Hadamard basis, and then in the second round, the verifier apply a Z gate, and in the end, the verifier send X to the prover. So for the single qubit setting, the way I present is the prover send the verifier always the same qubit, and I don't distinguish X basis or Z basis. So here you can see the first round is always about X, and the second round is always about Z. But for the many qubit setup, it's just going to be the first round, the verifier measure Z and apply Z and measure Z, and the second round is also about Z because the prover already did the measurement for you. Okay. And here is just the way we formulate a malicious prover. And as you can see in the last round, you are going to have OX and OZ. And that's how you are going to obtain anti-commuting. So let's analyze the first test. So you can see the equation I gave here. If the measurement result of the first round is the same as the measurement result the prover send you back in the last round, then this equation is exactly the equation you are going to have if you do the proof. I think it's also kind of easy to understand this. It's quite intuitive equation, like make a lot of sense. So I use this diagram to represent this. So putting x in the first row is the same as putting OX in the last row. And similarly, we have the Z consistence. Putting OZ in the last row is the same as putting Z in the second row. And the same for the third test. And the last test is a bit tricky because the equation you are going to have is you first apply Z in the second round and then you apply OX in the last round. It's the same as you apply X in the first round, Z in the second round, and -1 in the last round. And once you put everything together, if in the beginning you start with OX, OZ, and the first step you can move one OZ to the second round because OX apply in the end. So like in the equation it never mind. And then once you move Z to the second round, you can flip the X to the first round by using the first test. And by the consistent set in the third round, you move the Z in the second round to the third round. And then you move everything back to the last round and you get the anti-commuting relationship in the single qubit setting. And once you have this, you can extend to many qubit just by using Hadamard code. You are going to have anti-commuting relationship for all the n qubits. Yes, and then you have the ability to measure any XA term or Z term. Still, you need to play more trick. Like so the whole protocol have the anti-commuting test as the first 3 rounds, and then you have a few rounds later. For example, one round can be right. So I think you can add a 4th round where the verifier send the prover XA and ZB. And you add 2 more consistency tests. One test the consistency between the first round and the 4th round to check whether the measurement for the X basis is consistent. And another test to check the second round and then the 4th round is consistent. And then you can get measurement under 2 bases together in 1 round for the first round. And then you can test like our toy Hamiltonian. Yeah. I believe you will have many questions, so please ask me questions.